A picture can say 1,000 words. The brilliant yellows, the deep blues, the lively reds, how did their creators manage to paint such hues which evoke such deep emotions in us? The answer is simple. They got the mix right, a precise and accurate mix of different colors on their palette. Yellow with just the right dash of white and red, and Van Gogh had forever changed the way the world sees sunflowers. Like these paintings, chemistry too has changed the world around us, and curiously enough, it too is about getting the mix right. Hello and welcome. It's great to have you with me on this expedition into the chemical world. So where all will this expedition take us? We will look at the importance of chemistry in daily life. We will also learn about SI units, its multiples and submultiples. We will then differentiate between precision and accuracy in measurement and discover the importance of scientific notations and significant figures. Finally, we will take on exam questions in Exam Decoded. You know the famous scientist John Desmond Burnell once quipped, "All that glitters may not be gold, but at least it contains free electrons." Chemistry in free flow action all around us. In our household appliances, in the food that we eat, boosting crop production through fertilizers, in fighting diseases with medicines, in propelling rockets into space, or even in saving the environment by finding safer alternatives to the hazardous CFCs or chlorofluorocarbons. If you look at it, all of this is matter governed by the laws of chemistry. Chemistry deals with the composition, structure, and properties of matter. It addresses these questions in terms of basic constituents of matter, atoms and molecules. In other words, chemistry is about compositions. And when we talk of compositions, it becomes vital that all measurements of constituents of a particular composition are accurate and precise. Here is a mind bender. What if I asked you to provide me with 20 dilute sulfuric acid? 20 what, Debu? You'd ask, and I would have you exactly where I wanted, waiting to be told the units of the quantity of acid. But if I said I needed 20 milliliter of dilute sulfuric acid, you would be able to give it to me in a flash. So you see, without the unit in a number, quantitative expression is incomplete. In fact, without units, some of you could have given me 20 drops of acid and some of you 20 beakers. So, what are these units and how are they standardized for all measurements across the world? Units, like the milliliters we used for the acid, have been set by the International Bureau of Weights and Measurements. Based on the metric system, these are the International System of Units or SI units. The Bureau devised an International System of Units or SI units comprising 7 basic units. I am sure you are familiar with most of them. Take a look. As you can see, they are represented with their physical quantities and symbols. There are SI units for mass, length, temperature, amount of substance, time, electric current, and luminous incandescence. Just like there are rules for grammar and spelling, there are also rules for using SI units. the unit is written to the right of the quantity and there must be a space between the two. You will need to be careful about these rules when you do calculations involving SI units. Now, calculations in chemistry can range from computing massive numbers like those in nuclear reactions to minuscule quantities like the size of an atom. So it becomes important to learn about the multiples and submultiples of base SI units like meter. These multiples are represented in increasing powers of 10. Now, if you look at this chart carefully, you will see that the factor of 10 increases from 1 to 18 along with prefixes from deca to exa. This chart represents quantities that are larger than the base SI unit. For quantities less than the base SI unit, the powers of 10 go from -1 to -18. The prefixes go from deci to atta. So if you are measuring a large quantity, say the actual distance between Delhi and Agra, what prefix would you use? You would use the prefix kilo, which is represented by 10 raised to power 3. But if you were to measure the distance between the two dots that represent Delhi and Agra on a map drawn to scale, then you would use a prefix for smaller quantities like centi, which is represented by 10 raised to power -2. So prefixes in SI multiples and submultiples are chosen depending on the quantity to be measured. Converting these quantities from one to another is just a question of adding zeros according to the powers of 10. And moving decimal points in the correct direction according to the power of 10. Now sample this. What will be your height in centimeters and nanometers if you are 1.8 in SI unit? As you know, meter is the SI unit of length, so your height is 1.8 meters. Now, 1 meter is 10 to the power 2 centimeters and 10 to the power 9 nanometers. Therefore, if I were to express your height in centimeters, it will be 180 centimeters, and in nanometers, you will be 1.8 into 10 to the power 9 nanometers. As I had said before, sometimes the numbers we deal with can become extremely huge, like this one for example. This number is called the Avogadro number and represents the number of atoms or molecules in 1 mole of a substance. It's used in scientific calculations. The same number can be expressed in scientific notation by 6.022 times 10 raised to power 23. 6.022 is called the coefficient. To write very small numbers, we use negative exponents. For example, the diameter of a carbon atom is about 0.0000000001 meter. In scientific notation, it is 1.0 times 10 raised to power minus 10 meters. Remember, a positive exponent indicates a number larger than or equal to 1. A negative exponent indicates a number less than 1. Time for our very own SI, that is Super Intellect quiz. If you think you come under this category, then answer this. Although the prefixes micro and mega imply opposite quantities, what do they have in common? I am taking a short break now, but I'll soon be back with the answer. So stay tuned. Welcome back. Before the break, I asked you a question. What is common between prefixes micro and mega? Are you ready with your answer? The answer is 6. Mega is 10 to the power 6 and micro is 10 to the power minus 6. I am sure you are now clear about the concept of units of measurement. But these units are of little use unless measurements are done with precision and accuracy. Take a look at what can happen if precision and accuracy are missing from a measurement. Two men measure their heights in two separate rooms. Both believe they are 6 feet tall. But look what happens when they get together. Maybe if they had focused on precision and accuracy, they wouldn't be so surprised by the results. Precision indicates how closely repeated measurements match each other. Accuracy indicates how closely a measurement matches the correct or expected value. For a better understanding, let's join some friends of mine at a game of darts. We can see that the arrows that strike closer to the bullseye are considered more accurate. When all the arrows are grouped tightly together, the cluster is considered precise. Of course, you can tell who won, can't you? Now, in chemical calculations, a result is only considered valid if it is both accurate and precise. In order to ensure this, we must learn about significant figures. These are numbers that are known with certainty. I have this notebook here in which I jot down all my scientific musings. Although I use it day in and day out, I never ever got down to measuring its width. Let me do so now and see if I can arrive at an accurate and precise significant figure. I guess I am distracted because all 3 times I've got 3 different widths. How will I know which one is the most accurate? This is where significant figures come in. As you can see in the first measurement, we have only 2 significant figures because the 0 at the end is not counted as significant. The second measurement has 3 significant figures, so it must be more accurate. The third seems to be the most accurate. Why? Because it has 4 significant figures. So I can safely conclude that this notebook is precisely 215.6 millimeter wide. Are you wondering how I decided which numbers are significant and which aren't? Don't worry. Here are some rules that tell you exactly how. All non-zero digits are significant. Zeros in the middle of a number are significant. Zeros to the right of a digit after a decimal point are significant. Zeros between a decimal point and a number are not significant. Mathematical functions with significant numbers have their own set of rules. Whenever we add or subtract numbers with significant figures, the result cannot have more figures to the right of the decimal point than either of the original numbers. Let's add these two quantities, 73.3 gram and 2.435 gram. The total comes to 75.735 gram. Now, the final answer should not have more figures to the right of its decimal point than either of the original numbers. So, it can only have one number after the point. After rounding it off, The answer then is 75.7 grams. Multiplication and division with significant numbers is slightly different. The answer cannot have more significant figures than any of the original numbers. Here is a numerical problem. A person weighing 75.3 kilograms gains 21% of his weight in a month. According to my calculator, the gain in weight is 15.813 kilograms. Since 21 has only two significant figures, we must report weight gain by rounding it to two significant figures. So, the total weight gain is 16 kilograms. Let's now go over to a young caller who has a question for me.
My question is, I'm still not clear about the addition rules. Why is the sum of 5.67, 1.1 and 0.9378 7.7 and not 7.7078?
Okay, no worries. Let me tell you why. Now from all three original numbers that you have mentioned, 1.1 has least significant figures, that is 2. That's why the actual sum 7.7078 is rounded off to two significant figures. Therefore, 7.7 with one decimal place is the answer. I hope that clears your doubt. Always remember, whenever we add or subtract numbers with significant figures, the result cannot have more figures to the right of the decimal point than either of the original numbers. Someone once said that reason can answer questions, but imagination has to ask them. I think I would be making an accurate statement if I said that this is precisely the time to take a break. But do come back as I give you some important tips on handling those tricky exam questions. Welcome back. Let's take a look at the main points from today's show. Today we have learnt about the importance of chemistry in the world around us and have also learnt about base SI units. We then saw how prefixes for multiples and submultiples of SI units are chosen depending on the quantity of measurement. Finally, we practiced how to determine significant figures and their scientific notations and learnt the rules for measuring with precision and accuracy. Time now to speed into Exam Decoded. Welcome to Exam Decoded. Now it is time to measure your accuracy and precision in this topic. Are you ready to take on those important exam questions? Brace yourself for this rapid-fire round. Let's quickly go over the rules. This round has 5 questions, each of which you must answer in 5 seconds. You will either have multiple choice questions or you will have to spot a statement as true or false. So let's play together and see how we go. Here is your first question. Give the correct number of significant figures for 4500 and 0.4500. Your options are A. 4 and 4, B. 2 and 4, C. 4 and 2, and D. 2 and 2. The right answer is option B. 2 and 4. Because only non-zero digits are significant and also all digits including zeros to the right of a decimal are significant. On to the next question. What is the SI unit of temperature? A. Centigrade, B. Fahrenheit, C. Kelvin, D. Degrees. The correct answer is C. Kelvin. That was quite easy, wasn't it? Coming to the third question, true or false? Precision is how closely a measurement matches the correct or expected value. If your answer is true, then you are wrong, as precision actually indicates how closely repeated measurements match each other. So the correct answer to my question is false. Second last question, and it is a tricky one. Is it possible to have a value of exponent 10 to the power 0? Yes or no? The right answer is yes. 0 can be an exponent. 10 to the power 0 would be equal to 1. I hope all of you are keeping a tab on how many you have got right, because we are going to tally our scores in the end. Last question. Give the answer to the correct number of significant figures in 1.367 minus 1.34. A. 0.03, one significant figure. B. 0.027, two significant figures. C. 0.02, one significant figure. D. 0, no significant figure. The right answer is option B, 0.027, which has two significant figures. They are 2 and 7. That ends our rapid fire section. It's now time to compare scores. If you have got all 5 correct, then you are our topper high flyer. If you have scored 4 or 3 out of 5, you are an achiever. And anything less than 3 makes you a learner. I am sure we have many high flyers and achievers out there wanting to fire away at more such questions. And all of you learners, don't sweat, because there is plenty to practice on www.topperlearning.com. So do log on to improve your scores. Okay, that rapid fire section sure got my pulse racing. Now I'd like to tell you about another significant figure. The topic, some basic concepts of chemistry, has a weightage of 3 marks in your examination papers, and therefore we would rate it important for your preparation. So let's see what questions you can expect from this topic. You are likely to be asked short answer type questions of 1 or 2 marks, and most of these questions will test your conceptual ability. That is, they will test how well you use theoretical concepts to solve problems. Let's take up one of the difficult conceptability questions and see how we fare. And don't get too disturbed by the word difficult, because in our dictionary, difficult is just another way of saying that it's not ridiculously easy, right? So here is the question. Give the significant figures and scientific notation for 0.00682. In the exam, this would be for 1 mark. If you remember, according to the rules for calculating significant numbers, in 0.00682, the leading zeros are not significant. So, the number of significant figures is 3, and the scientific notation is 6.82 times 10 to the power minus 3. That was not so difficult after all, was it? Well, if you want to get significant marks in your exam questions, then pay close attention to what today's expert is going to tell us.
In this chapter, one needs to keep in the mind the SI unit for various measurements and the abbreviation of units. For example, kilograms is written as kg and meter is written as m. You should also remember that the units are always written on the right hand side of the number. It is very important for you to remember the rules for determination of the number of significant figures.
Well, it's a wrap on today's show. So to all the budding chemists out there, here is a parting shot. Why are chemists so great at solving problems? Because they have all the solutions. So keep striving for those solutions. Until next time, goodbye.